Welcome back. Now we will talk about groundwater and karst aquifers. We will start with section 3.11 in your textbook. We skipped section 8, 9 and 10 in your chapter 3. So here we will answer first these two questions. What is the importance of groundwater? Where is groundwater distributed? And how does it move through the subsurface? So first let's understand why groundwater is important. Groundwater is the largest reservoir of fresh water readily available to humans. So here pay attention to this term, readily available to humans. There is another reservoir of fresh water, but that is not easily available. It is not economically feasible to draw water from that reservoir, and that reservoir is glaciers. Groundwater fulfills 40% of water need globally. Drinking water for over 50% of population. 40% of irrigation water comes from groundwater. 25% of water used in industry. So groundwater is the water that flows beneath the surface of our earth. So the like we saw earlier, after precipitation the water is absorbed below the ground, and that's where it starts flowing underneath the ground, and it makes groundwater, the water that is found below the surface of ground. Even though it's not easily visible or known to us, but that is the largest reservoir of fresh water which is easily available to us. There are a couple of negative or points for groundwater. One is overuse can cause stream flow depletion. Another is land subsidence, and there is increased pumping cost if the water level goes too far below the ground. Important geological agents form sinkholes and caves, stabilizes the stream flow. Groundwater, we will see after a few slides that how groundwater is responsible for one of these very dominant geological feature called sinkhole and caves, which is very common, especially in the state of Florida. If you go like in the state of Texas, state of Missouri, Kentucky, it's very common, these sinkholes and caves. It's not all over the entire US, but it is scattered in different region or parts of United States, and it all depends what type of bedrock is in those geological area where you find these sinkholes and caves. Especially in the case of the state of Florida, the entire state of Florida is sitting on carbonate aquifer or carbonate rock, and that's the reason we have so many sinkholes and caves, because these carbonate rocks have a tendency to dissolve as the water flows through them. So over the years, these dissolution features grow larger and larger in size, and they become like large caves or sinkholes over the time. Another important function of these groundwater, that it stabilizes the stream flow. Stream flow is another term for surface runoff, or the water that flows in the stream or river. So lots of time these groundwater flow, it emerges out on the surface and it meets with this stream flow, and we will also see where and when it happens. So then it stabilizes the stream flow. So when the groundwater meets with the surface water, and if there is any mass imbalance, like if the water level is dropping in the stream, then the stream will gain water from the groundwater, and if the water level is too high in the stream, then the groundwater will gain water from the stream flow. So this is how it stabilizes stream flow or surface flow or runoff. Here is a very good schematic. It shows the importance of groundwater, why we need to preserve groundwater, why we should protect it, how it is a very useful natural resource. This is on the left side. This shows your total global water resource which is available to us on our planet Earth. 96.5% is in the ocean. So majority of the water is saline water, not something we can use for our industrial use or domestic use or for irrigation or any other need. So majority of the water is there in the ocean, and it's very small percentage which is fresh water, right, which is 2.5%, and out of this 2.5%, majority is again trapped in glaciers and ice sheets, so not something that we can economically draw. It's not possible, or I mean economically not possible to put a pipeline to get water supply from by melting the glaciers or ice sheets. And so again, out of these 2.5% freshwater reservoir, 68.6% is trapped in glaciers and ice, and the remaining 30.1% is in groundwater, and then there is very small percent, 1.3%, something that we see in rivers, streams, lakes, or ponds on the surface of water. So that's how you know that groundwater is the most dominant reservoir of fresh water, which is easily available to us. So if somebody asks you what is the most dominant reservoir of water, only water, then you call it ocean. But when I add this term fresh water, then you would answer groundwater is the most dominant reservoir, which is easily accessible to human for fresh water. Okay, so there's a small distinction. Ocean is the largest reservoir for water. Groundwater is the largest reservoir, or which is easily accessible for human need. Largest reservoir for fresh water. Okay. Here are a couple of pictures. This is from Mammoth Cave in Kentucky. You can see these are some of the dissolution feature inside the cave. So this is something we are looking below the ground. This is not on the surface of the ground. Somebody had to go into the cave and take these pictures, right? So you can see these dissolution features, how these carbonate rocks or the columns are coming down from the ceiling of this cave, and then there is another column which is rising up from the surface toward the ceiling. So we will see how these dissolution feature forms inside the karst, sinkholes, or caves. The one below that, this is another photograph. This is more like a satellite picture in New Zealand, and these dots are the sheeps. So these sheeps are grazing in the open ground, and these patches that you see here, these are the sinkholes or depression due to the dissolving rock underneath. So you have these karst or carbonate aquifer under this landscape, and that landscape is dissolving as water flows through them, and then it creates these depression or sinkholes kind of feature on the surface of ground. So how does groundwater come into existence? It comes from infiltration of rainfall into the ground. So after the rainfall event, some of the water flows on the surface in the form of a stream or runoff, but another part of rainfall is absorbed into the ground, and its amount is influenced by slope, surface material, which is the permeability, if the surface is paved or not, intensity of rainfall, how much rain occurred, for how long it occurred, and then vegetation. So these are the four factors that controls the quantity of groundwater, or the water which is absorbed into the ground after rainfall event. Belt of soil moisture. So this is the belt of a small thickness of water which lies near the surface of the ground. So this is like a small vegetation like grass. They hold some of these water molecules in their root, so that creates a small belt of soil moisture. And then there is a zone of saturation. This is a zone below the ground where the entire soil mass or the pore space is filled with water or groundwater. The upper limit is called water table. So you can think about the soil. So suppose this is any soil mass. So you have all of these solid particles, and then you have pore here, right? So you have open space here, and in lots of cases this open space is filled with air. So these are the things that can fill it: air, water, gas, oil, or hydrocarbon. So these are the different material that can fill these pores. So when it is filled with air or gas or oil, we call it unsaturated. And when it is filled with water, then we call it saturated. When the entire pore volume, so this one is pore or pore volume, and when this pore volume is completely filled with water, then we will call it saturated. So that is how it creates the zone of saturation. So after the rainfall, so suppose this is your ground, after the rainfall you have this cloud here, rain happens, and then the water is absorbed below the ground, right? So this water keeps on percolating downwards, right? By gravity it keep on going downward, and below the ground somewhere you have impermeable layer which does not allow the water to percolate any deeper. So here the water will start to accumulate, and as you have rainfall events continue, this will fill up this zone. So this is your zone of saturation, where your pore is completely filled with water, and the top surface of this zone of saturation is called as water table. Okay, and of course this water table, you can imagine, this will fluctuate seasonally. As you have more water rainfall event, this water table will rise up, and during the dry season this water table will go down. And lots of time as a human, we drill well and we pump water out from this zone of saturation. Area above the water table is called the unsaturated zone, because this is where the pore space is not 100% filled with water. It has some water, and then it has some part of the pore which is still saturated with air or some other mass which is not water. So then we call it unsaturated zone. Water table is irregular. Groundwater moves slowly. Water piles up between stream valleys. Variations in rainfall, changes in permeability of sediment. So these are the factors that controls the level of water table. Water table falls during drought or during the dry season. Porosity. Porosity is an important term. I want you guys to definitely remember this term. Porosity. This is volume of pore divided by total volume of rock or soil. Right. So this is what porosity is. It is a percentage volume which is occupied by the pore in any rock or in any soil. So even in the rock, it is a porous material. It is it may look like a completely solid impermeable material on the surface, but if you put it under a strong microscope, then you will be able to see all those minerals, how they are separated, and how there are these pores all over the place. So porosity, total volume of rock or sediment that consists of open pore space. So this represents the percentage of opening or pore space available in any rock. So you can think about this. The porosity, its value goes from 0% to 100%. So 0% is when you have zero porosity, it is completely full, so there is no pore here, so this is what it will be like. And 100% is when it is a complete, it's just a big hole in the rock, so then it will make it 100% porous material. And if the value ranges between 0 to 100%, the value which is close to 0%, that will mean low permeability, or sorry, low porosity. So low porosity, and the value which is near 100%, that will mean high porosity, right? And you can imagine its effect on the flow of water, right? When there is low porosity, then it means it has very tiny pores here and there in very small quantity, and when water flow through this such a medium where you have such a small pores, then the water will flow very, very slowly, right? On the other hand, when you have a domain where you have these large pores, right, then the water can quickly and rapidly flow through them, right? So this is the difference, this is the effect of porosity on the flow of water. Spaces, porosity is also defined as the spaces between particles, joints, faults, dissolution cavities, or vesicles. Depends on size and shape, packing and sorting of grains. So it is strongly a function of the grain size, and that makes up of that soil or the rock material. So you can, again, another photograph we can draw here, might have seen it before. If you have all of these sediments of the same size, very large size, see, so now it will leave all these large pores here. If they are all of the same size, uniform size, that will leave a lot of pores. But think about this, if we now start fill it with the small sediments, now that will start filling up these pores quickly, the small spaces are now filled up quickly. So if you have all these particles of varying size, so that rock or that soil will have very low porosity compared to a material that has all the minerals or the grains of the same size. So if you have large variation in the grain size in your rock or soil, then the porosity will be low. 10 to 50% in sediments. Quantity of groundwater depends on porosity. So like we discussed earlier, that how a lower porosity makes it very difficult for water to flow across it, whereas the higher porosity makes it much easier and faster for the water to flow across it. So the quantity of water which is absorbed into the ground, it is strongly dependent on the porosity of that ground surface. Permeability, it is another important term. I definitely want you guys to remember these two terms, porosity and permeability. Porosity indicates the percentage of volume or the open volume, percentage of open volume present in a rock. Permeability, it is the ability of any material to allow the fluid to travel across it. So how easily a material would allow water to flow across it, that represent that easiness represents the permeability of that material. So that permeability now will define these two terms, aquifers and aquithards. So aquifer, you guys must have heard of this. This is a very common source of drinking water from the groundwater resource. It is a type of rock or sediment that water can move through easily. It is made up of sand or gravel. So the main idea is the water can easily move across this rock. So such type of rock are called aquifers. And then exact opposite is impermeable layer, or a type of rock that does not allow the water to move easily across itself. So those type of rocks or soil are called as aquithards. Clay is one example of aquithards. Sand or gravel are example of aquifers. Here's a very good schematic of a groundwater system. So this is here, this is your surface, ground surface, and you can see that this blue shaded region, this is your water table. So the top surface is water table, and this entire blue shaded region is groundwater zone. So here, if you zoom in at any soil particle, or group of soil, then you will find that that pore is 100% saturated with water. So this is why it is called as zone of saturation. But if you zoom in at anywhere above the water table, that you will see that partially it has some water molecules, and then majority of the pores are not filled with water. It has air or gas or some other material, but not water. And if you drill a well which is deep enough, which is deep into the groundwater, not groundwater, it is not deep enough to reach the water table, so this will be an unsuccessful well. Whereas if you drill this another well that goes deep into the groundwater below the water table, then that will become a successful well. This one here, you can see in the middle you have this acutard. So we just saw that acutard is type of a rock or sediment that does not allow the water to flow across easily. So what will happen, a ponding will happen, the water will start to accumulate above this acutard, and you have this purged water table. This is not a full water table, because here you can see that water table is actually this one where majority of the groundwater is available. So this is a very localized kind of a ground water zone of groundwater, and it has a term called purged water table. And over there also, if you drill a well, it will become a successful well, but it will provide only limited supply of groundwater compared to the entire zone of groundwater. So this is here showing the main water table, and here you can see that how groundwater in some places it can come up on the surface and meets with the surface water stream. So this is also another location. So you can see here, if you look into the third dimension here, this purged water table goes into the third dimension, and wherever there is opening on the ground, it will come out or emerge on the ground surface in the form of spring. So this is how the groundwater and surface water meets. So now this spring will converge toward the nearest river system and become part of it. So here one is by spring where the groundwater meets with the surface water, another one where the groundwater itself come up, emerge on the surface and directly meets with the surface water stream. So this is a very good representation of the entire groundwater flow system. So it has the surface water, it has an actual groundwater table, saturated zone, unsaturated zone, when and how you can have a successful or unsuccessful well. Groundwater moves slowly from pore to pore. Typical rate is a few centimeters per day. Moves from high water table to low water table because of gravity. Usually towards a stream channel, lake or a spring. Pressure increases with depth in zone of saturation. So if you just look at this zone of saturation, if you go deeper in this zone of saturation, the pressure will increase, which is called as hydrostatic pressure. When the water is just sitting somewhere, it has a pressure. Deeper you go in the water, more pressure you feel from the overlying water or the layer of water. So that is just a hydrostatic pressure. So pressure increases with depth in zone of saturation. This is another interesting streamline. So these are called a streamline, the path the water molecule takes below the ground. So if you just track those paths taken by the water molecule as they are flowing below the ground, this is what it will look like. You have these surface stream, and then you have infiltrated water. So infiltrated water is coming downwards under force of gravity. It is pulled downwards, but it has a higher potential here compared to this one, the surface stream. So the water which is at higher elevation has higher potential. The water which is at lower elevation will have lower potential, and it is a natural law of nature that water flows from higher potential to lower potential. or another words you can say the water flows from higher ground to lower ground. So here there are two forces acting. If you look at this schematic, one force is the force of gravity, which is trying to pull the water molecules vertically downwards, and then there is this another nature force of nature which is trying to move the water from higher ground to lower ground. So that is how this water path or trajectory turn like a loop around here until it meets with the surface water stream. So that is how we have this curved surface because of these two counteracting forces acting on these water molecules. One is the vertical downward force of gravity, another one is this difference in potential which is driving this water from higher ground to the lower ground. What is the importance of groundwater? Let's review this question quickly. Largest accessible reservoir of fresh water. Where is groundwater distribution and how does it move through the subsurface? It surrounds grains in the belt of soil moisture and fills pore space in the zone of saturation. It moves slowly from pore to pore because of gravity. Just remember, gravity is acting everywhere and it tries to pull everything vertically downwards. What are some features that results when groundwater reaches the surface? How else does water reaches the surface? So now we will look at these interesting geological landscape features that is formed due to the interaction of groundwater with this dissolving rock. Spring, we just saw in this schematic how sometimes the groundwater comes out on the surface where the and comes out or eject in the form of a spring. A spring is a natural outflow of groundwater, occurs where the water table intersect Earth's surface. Aquitard prevents downward movement of water. So that is why the water has no way, since it cannot be pulled downward by gravity anymore due to the presence of this aquitard. So the only way out for this groundwater is to come out on the surface, and that is how the spring is formed. A perched water table is a localized zone of saturation above an aquitard. These are some of the photographs of these are springs, and then you have these large kind of a lake here, and this is also connected to the groundwater. Hot springs are warm because groundwater circulates at depth. Temperature increases about 2 degrees Celsius every 100 meter. So if you again think about below the surface, as the water is flowing, it is flowing at certain depth, and as we go deeper in the ground, every 100 meter the temperature increases by 2 degrees Celsius. So that's why the groundwater that we pull out from the ground from below ground, it is generally warmer than average annual air temperature. Geysers are the columns of hot water and stream ejected with great force. Underground chambers full of water are heated and expand. So these are special type of springs, you can say, where the water will come out on the surface with full force. So this is I will just try to explain it quickly here. So think about of this now, as this is your ground surface, and very far below here, suppose you have a magma chamber, right? So we will see all this detail about magma chamber in the next chapter when we will look at plate tectonics. But for now, just know that in different part of the interior of the earth, at different location, we have these magma chambers. So magma are these very hot molten rock. So below the ground it's extremely hot, and sometimes it melts. How hot it is, the rock can melt. So this will create magma chamber, and when this groundwater, right, so this groundwater is percolating downwards, it is coming down, and as it comes in contact with this magma chamber, this will cause some heating, right? So it's a very hot Sometime it is around 1200 degree centigrades. So you can imagine how hot the water will get. So when the water gets hot here, this hot water will start rising toward the surface because of buoyancy. So this is another law of nature, that the lighter mass always rises toward the surface. When you mix two different masses of two different density, the lighter mass will rise toward the surface. So this hot water, it is relatively so this is not cold but relatively cooler compared to this water. So this one will be heavier, and the water which has just come in contact with the magma chamber, it is a hot water, so it will start rising toward the surface. So this cycle will continue. The water keep the cool water coming down, and this hot water, it will keep rising, right? So as it rises, this water, the volume of water will continue to increase, and a point will come where it will increase, where it will eject in the form of geyser, right? So when this water will eject, this kind of chamber will be empty now. So now more cold water will rush in here, and while it is rushing in here, it is passing through this hot region, and it will again start to fill up this region, and when it has enough water, it will again start rising and then eject in the form of geyser. So it is not a continuous release of water, but it happens intermittently after some time, 15 minutes, depending on how long it takes to cool to boil this water hot enough so that it can be released with full force on the surface. So that is what geyser is. A well is a hole drilled into the zone of saturation to remove groundwater, as we saw earlier in the schematic. So this is going vertically deep into the ground, vertically downward into the ground, and the purpose is to draw water by means of pumping. So when you pump water, there is a depression of this water table around the pumping region, and that depression is called as a cone of depression, right? And this drop in water table is called as drawdown around the water table. So if this is your around the pumping well, so if this is your pumping well and you're drawing water out, that will create this cone of depression, and this drop in water table around the pumping well is called as drawdown, the drop in the water table. Okay, so these two terms, I want you guys to know that: drawdown and cone of depression. So cone of depression is this depression is the zone created around the pumping well during the pumping, and drawdown is the drop in water table due to pumping around the pumping well. Artesian system, this is there are two types of aquifers. One is called as confined aquifer, another one is called unconfined aquifer. So here is one example of confined aquifer. It's a very good schematic. You can see these two, the brown layer here on the top and bottom, the blue shaded region is your groundwater. Okay, so this layer, the brown layer above and below, these are aquitard. So it is impermeable, it does not allow the water to percolate across this layer. So this zone of saturation is not getting recharged from up above because the recharge cannot go across this aquitard. So the aquifer itself is laid out in such a way that it is exposed to the ground surface at some place, so that the rainwater will feed into that landscape, and then the water can be absorbed into this aquifer system, and then it can travel much farther from the site where the rainfall has occurred. So this is where, if you zoom in here, you can see this is the recharge area where this aquifer system has become exposed near the ground surface, and it is being recharged here, and as it is flowing downwards, right? So now you can look at this again. Remember that's law of nature, where the water flows from higher elevation to lower elevation. So here you can see this recharge area is at a much higher elevation compared to rest of the aquifer. So now if you drill a well here farther from the recharge area, now this well will come out of the ground, and here this well is still, the tip of the well is still far below this top point of the recharge area. So the water will come through here and it will just come out itself without any pumping. So this is what happened. This is one example of flowing artesian well. Here if you drill a well, the water will start coming out by itself without any need of pumping, and that's just because of that principle we discussed earlier, how the water tend to flow from higher elevation to lower elevation. So couple of terms here. This is called confined aquifer because it is confined on top and bottom both sides. Okay, and these top and bottom impermeable layers are called aquitard, and then this pressure surface is that pressure line which goes parallel to the ground surface, but its peak is at the recharge area where the water is recharged into the aquifer system. So this is once again the review. What are some features that result when groundwater reaches the surface? Springs, pursed water table, and hot springs. How else does water reach the surface? Geysers, wells, artesian systems. What are some environmental problems associated with groundwater? So now we will see some of the challenges and why we must preserve and protect the groundwater. Groundwater is a natural system in equilibrium, and it is considered as not a renewable source. So once you draw the water out, it is not considered as renewable, even though we saw that how the rainfall recharges the aquifer system, but the time it takes to refill or recharge the aquifer system runs into thousands or millions of years. So every aquifer that we have distributed all over the world, it has taken about thousands and thousands of years for all of those aquifers to become saturated with water. So if we think about if we empty those aquifers in current time, then it will take thousands and millions of years for them to be replenished. So that's why the time that it takes to replenishment is so long that we will consider it as a non-renewable resource. Ground subsidence occurs when water is removed faster than it is replenished, because you can imagine the water which is held in the pore in the subsurface aquifer system, those have some weight bearing capacity. It can hold some weight above itself. So if you draw that water out from the aquifer system, that weight bearing capacity reduces and the ground will start to settle. And this is what happened here in San Juan Valley. So this is where the ground used to be, the ground surface in 1925, which is almost about 90 years ago. And this ground has subsided about 30 feet in just 53 years. And that is due to urbanization, that is due to sudden burst of population migration in this region, and that led to this increased demand of fresh water resource for irrigation, for industrial, for domestic need, and that leads to excessive withdrawal of water from the subsurface aquifer system. And see, this is what the impact, the around 30 feet drop in the ground surface in just 55 years period of time. Another one is the contamination, the likelihood of the contamination of these groundwater resource. As we know that these groundwater runs everywhere below the ground. And we have septic tanks which are located all over the residential areas around the houses, and these septic tanks are also buried under the ground. So sometimes there are chances that these septic tanks can be corroded over the years, and then it can leak, and there are chances that the contaminant can be released from the septic tank and can find ways to meet with the groundwater. And once it finds ways to meet with the groundwater, then it can start spreading all over the neighborhood, or whichever place is using this water for drinking purposes. Right, so it can quickly reaches to the drinking water well, and that depends, that how quickly this contaminated water will spread. That again depends on the permeability of the aquifer through which this groundwater is flowing. So especially in the case of karst limestone, where you have these large pores or large fractures, then the water will quickly pass through this aquifer system, and very quickly, in just a duration of few weeks or few months, it will contaminate a very large area of landscape. On the other hand, if the aquifer system is not very permeable, then the water will flow relatively slowly, and it will take months and years to contaminate a large area of groundwater. So these are some of the environmental problems associated with groundwater, a non-renewable resource, ground subsidence, and contamination. So I want you guys to remember these. This is an important question, might show up in your midterm exam. How do karst and caverns topography form? So there is some geochemistry coming up. I want you guys to understand some of the reactions here. Most groundwater contains carbonic acid. And so how does that happen? CO2 dissolved from air and decaying plants. So especially after the industrial revolution, we are releasing a lot of CO2 in the atmosphere, right? This is your cloud. So this is your rain coming down, and this is your atmosphere. You have all these different gases here, right? CO2, sulfur dioxide, nitrogen dioxide, and these are all coming from these power plants, right? So you have power plants which are releasing all of these chemical gases into the atmosphere, and when the rainfall happens, this rainwater combined with these different gases in the atmosphere. So sometimes the equation goes like this. This is H2O is your water, right? CO2 plus H2O. This is actually, I should write it like this. This goes in both directions, and this can combine with so this is what happens. So this is what you have, lots of this H plus ion. So when carbon dioxide dissolves in water, it produces protons or H positive ion, and that is what going to make your water acidic. So there is another term called acid rain, which is due to the increased concentration of H positive ion in the water. So as we increase the H positive ion in the water, the water will become more and more acidic. So this is why. Now look at this acidic water when it meets with when it falls on the ground, right? So now you have all of these. Suppose this is a carbonate rock, which is also called as karst aquifer. Carbonate rock, so this is what will happen. So carbonate, this is your carbonate rock, and it meets with H plus in the acidic water. The calcium ion will be broken away, and then this is the dissolution reaction, right? So this is where the dissolution will happen, and the acidic water will dissolve this carbonate rock, and then you will start forming these small pores will continue to grow over the times. They will continue to grow due to the process of dissolution, right? So they will grow even bigger and larger, and they will continue to grow, and under the ground we don't even know, as the water is flowing, these dissolution will continue, and they will become larger and larger in the size. And if you have any home here, so over the time there is a chances that this entire house will be engulfed by this sinkhole. So this is how the sinkhole form below the ground. Caverns formed due to the erosional work of groundwater. It has both physical erosion as well as chemical erosion. So the chemical erosion that we just talked about, due to this chemical reaction, the dissolution occurs, but over the time, as the dissolution continue, these pores become larger and larger in size, and as it become larger, the water can flow at a much rapid speed, and as it flows rapidly, it will have more energy, it will have more power to cause more damage to the surrounding landscape. So that will even further break these rocks more quickly. These are the two terms, stalactite and stalagmites. Stalactites are the columns which are projecting downwards from the ceiling, and stalagmites are these columns which are rising up from the surface towards the ceiling, and at some point they will meet together and make it a complete column shape. So these are the two features. So not only dissolution, sometimes the precipitation also happen. So this is the example where the precipitation is occurring. As the water is dripping down, the CO2 escapes, right? So look at this figure here, or the photograph. This is that a column, the vertical column, which is projecting downwards from the roof. This is called a stalactite, and here the CO2, as it escapes, this will lead to some precipitation of calcium carbonate. So addition of carbon dioxide will lead to dissolution. Removal of carbon dioxide will reverse the process, and it will lead to the precipitation of mineral. So as the water drips, the CO2 escape, and that will cause one mineral to precipitate. And over the years, and this feature takes about hundreds and thousands of years to grow in size, right? So as more and more water drips, more and more precipitation of this carbonate mineral will occur, and that will eventually form these vertical columns. So this is very common. If you have a chance ever to visit Kentucky, there are lots of caves and caverns here, and there are lots of I think visiting sites as well, a tourist site where you will find some tour guide as well who can walk you through these open caverns. So karst topography results from groundwater dissolution. It's common in Kentucky, Tennessee, Alabama, Indiana, and Florida. This is another example, another feature how groundwater or the surface water causes damage to a carbonate based aquifer. So this is unique in the case of carbonate aquifer. I want you guys to strictly, very clearly remember that this karst or sinkhole formation occurs only and only in carbonate based aquifer. It is not going to happen in any other aquifer, only and only in carbonate based aquifer, because this water can dissolve only carbonate type of minerals. Okay, so remember, this is another example where the surface water, as it is flowing on this carbonate based aquifer or bedrock, it is causing the dissolution. The dissolution will open up the valley, or kind of create a channel wider and wider over the time, and this valley will continue to not only widen, but it will also continue to grow deeper in the depth as the water flow through them. So now you will see some places you have springs, because the groundwater will start, as I said earlier, it goes from higher elevation to lower elevation. Due to the deepening of this channel, the ground there you can see this spring will start to emerge, and there are some of these sinkholes or collapsing sinkholes will start forming, sinking stream as the water is going into the ground, absorbed by the groundwater. So these are the different geological landscape that will form on the surface, and eventually it will meet with the groundwater surface. Sinkholes are depressions where limestone has been dissolved. Again, limestone is type of a carbonate rock. Calcium carbonate is its formula, chemical formula. Tower caps, karst landscapes have isolated steep-sided hills. So these are the special type of tower karst where the carbonate rock has dissolved in the surrounding landscape and will leave behind this kind of tower kind of landscape. Here is one example where the sinkhole has appeared under a residential area. You can see a sinkhole has absorbed or has engulfed, swallowed part of this houses. Luckily, rest of the houses still standing here, but it is not safe to continue to live in this house because it is likely that the sinkhole will continue to expand under the ground, and it might engulf or absorb this house in near future. How do karst and caverns topography form? Groundwater contains carbonic acid which dissolves limestone. So once again, remember that the karst and cavern feature only and only occur in carbonate based rocks due to dissolution of those carbonate rock as acidic water flows through it. That's it. That's the end of chapter 3. Just go over your textbook, the notes that I have uploaded that will help you understand the topic better, and I have uploaded some of the videos as well, so please go over those too. And that's all.